Okay. Okay, great. So we're going to get starting. I've just been talking about, prior to the break here, reminding folks of some of the things that we discussed in smaller groups yesterday concerning the support in any logic for sensitivity analyses through the use of parameter variation experiments. We had seen that we could define one-way or two-way sensitivity analyses quite easily using the features in the parameters area of the parameter variation experiment. It's notable that what is placed within this area are parameters within main. So if you wish to conduct sensitivity analysis with your model, you will want to be sure that those are declared as parameters rather than, say, constants, constant variables, static final variables in your model. Instead, you want to declare them as parameters, and it will give you this choice as to how to vary them for the model. Now, I also had noted yesterday that when conducting a sensitivity analysis, in many cases we want to perform for each of the values of the parameter a set not just of one realization but multiple. And in any logic, there's the support of what are called replications of a model, which basically allows you for each parameter vector, for each assumption about the parameters to be explored. Let's say when mean recovery time is 5 and mean duration of immunity is 10. For each of those possibilities, or in turn, separately, when mean recovery time is 5 and duration of immunity is 20, for each of those times to run the model a certain number of times, a certain number of realizations. So by checking this box, use realization, we can indicate we'd like to run the model, well, in this case, 10 times for each of those possibilities to capture within that given assumption about the parameters the effects of stochastics. Okay, and that's not an infrequent need which you use in combination with this exploration. Now, in order to do that safely, you will want to make use of this randomness area and make sure that it's selected random seeds. So when you run each of those 10, you actually get different results, not the same results. Okay. Now, a further use of sensitivity analysis is one which involves what are called Monte Carlo iterations of the model. And with that paradigm, one isn't going through and systematically exploring in a sort of gridded or hyper-gridded sort of fashion the different possibilities amongst these different parameters. Rather, one is iterating through with successive draws for each parameter of interest from distributions. So, for example, we might draw for mean duration of immunity. We might seek to draw the values of the parameter from a distribution. Let's say from a uniform distribution between 20 and 40. We do this in free-form mode rather than varied in range mode. And what this will induce is, as we run the parameter variation experiment, we will do so for different values of the parameter as drawn from a distribution. Now, in some cases, we have multiple lines of evidence that could point us to values of that parameter, and this would let us explore those, the implications of those in terms of outcomes. Okay, so we would simply, in the free-form mode, specify from what distribution, and in fact this is a Java expression, how do we determine the value of this? And we could do so for one parameter or for multiple parameters simultaneously, and then we specify the number of runs we wish to execute. In this case, we see the result of assuming, of running the model with random draws from each of these, where each one is run further 10 times. Okay? So it's still running it because there will be 100, as we say, iterations. Using AnyLogic's terminology, an iteration is associated with a specific parameter vector, and for each of those, it's running it 10 times over for 10 so-called replications in its terminology, 10 realizations. So in toto, between the 100 different parameter vectors and the 10 times for each of those 100, it's going to be running it 1,000 times. And that's what we see going on right here. We ran it through this, and this demonstrates that each of the so-called cores of our computer, each of the computational units that can be that can perform operations in parallel, is busy computing here. I believe on your computers you may have even more than 4 cores. Do you have 8? Do you see a larger number of bars yet when you run this? How many bars do you see? Is it 8? Yeah. Okay, so a computer with a large number of cores can execute these comparatively faster because each given run is independent of the other, so it can execute those in parallel. And once again, we see, even in the context of uncertainty about mean duration of immunity, there's certain regularities, certain things on which we could confidently anticipate given the structure of the model. Interestingly, you notice it's distinctly bimodal with a high central density region here, but there's a bimodal, a further mode down here, down close to 0, where essentially it dies out within this first trough and continues then at essentially 0 levels. Again, the information from this can be exported by right-clicking, saying copy all here. Right-click on this, copy all, and you can then go to a spreadsheet of your choosing. I'm actually not sure if it works for Google Sheets. I'm not aware of whether it has the facility to import it. But here I'm just importing it into, I did it on an existing sheet which has some dates in it. I don't want to do that. Here we go. So I'll import it, and what this is specifying is for different periods of time here on the x-axis, different intervals of time 11 to 12, time 12 to 13, for different numbers of individuals infected, how many of the runs had values which fell within those respective ranges. So for here, for example, from time 1 to 2, we had some runs which had, it looks like in terms of central tendency, 50 is the most single most common. 50 to 52 is the single most common bin. We have somewhat fewer down here, etc. Okay. So we can export those with only a modicum of difficulty, just like we can export data sets from this model, okay, from models like this. Okay. So sensitivity analysis, we can perform it very readily using the tools here, essentially running the model again and again. Now, sometimes we want to draw from something like a uniform distribution, a normal distribution, with a certain standard deviation, 5 and a certain mean, 30. Now, be aware that you got to be cautious about this in the sense of making sure that certain of the values don't turn out to be illegal. For example, you don't want a mean duration of immunity that's negative. So we'll often end up putting limits. So we'll take the max of 0 in this. So if this thing is less than 0, if the draw from normal, we'll just use 0, for example. Any logic does have, additionally, a thing called limit, okay? And what limit does is it allows you to limit from the upper side and lower side, or purely one or purely the other, the a value, so it'll truncate it. And it's perhaps a little bit simpler than using max and min to impose these limits. Max to impose a limit on the lower bound, and min to impose a limit on the upper bound. So you should be aware that there is a limit a function that you might want to use to sort of limit things between 0 and 1 or what have you. Unfortunately, in this item, autocomplete doesn't work, so you might want to refine your expression elsewhere and then go copy it in to this region, okay? Okay, so there's a little bit about Monte Carlo sensitivity analysis here. I'll just make a few more remarks on the basis of slides. Sensitivity analysis is a very broad topic. We can conduct it in multi-way or one way, whether we draw it from Monte Carlo analysis or a single time series, or in fact multiple, such as varying these things at the same time. There's a question of to what degree we're examining stochastics, or where we have ongoing changes over time. A further issue here concerns the idea of performing sensitivity analysis not just with parameter variations, a variation of parameters, but also with the structure of the model. Sometimes we wish to turn on and off a certain transition, or enable or disable a certain asymptomatic state, for example. So we posit everything as symptomatic versus asymptomatic. Or we posit a large reservoir of undiagnosed individuals versus not. Be aware that some of those, like turning on and off a transition, you might be able to accomplish by changing the values of parameters. After all, you could change a parameter value for a hazard rate of transition to 0 and thereby disable that. But sometimes we want to simply have a Boolean that indicates whether or not we wish something to be disabled, with true or false, and we'll make it a condition of a transition, as to whether you can transition to that on the so-called guard. That will indicate whether or not it needs to be true. Yeah. Yep. Okay. Yeah.
For all of those that are staying tomorrow for the project day, we are ordering food from the Chopped Leaf. So they have a variety of wraps and salads, of which I printed off copies. And so if you could write your name in, what the title of the product you want is, whether you want it to be a wrap or a salad, and your choice of protein, and that could be anything from grilled chicken to tuna to smoked tofu to prawns or wild salmon. And then I will gather it up and I will make sure that lunch is ordered for tomorrow. So I'm going to let Jeff start. Okay. And if you could just pass it around the room, and I will grab it up later.
Great.
Okay.
Thank you so much, Christine, as always. Okay. So it may be that for some of your investigations, investigating structural sensitivity analyses, enabling, disabling parts of your model, will be an important asset. As I noted yesterday, performing sensitivity analyses with models is an essential thing for both learning and for prioritizing your work, getting a sense of what parameter uncertainties, what uncertainties about the empirical evidence are important, and developing confidence on the part of reviewers you've done a really thorough analysis. So, elements of model uncertainty associated with the structure of the model are very important to often examine as sort of alternative dynamic hypotheses about what's going on in terms of natural history of infection or what have you. We'll have a chance probably later in my big data talk to talk a little bit about methods that involve updating a model with incoming data and dealing with uncertainty there. Much of our comments here have been with respect to static uncertainty, where we assume a certain thing for a parameter on an ongoing basis. And there's a variety of diagrammatic tools we have that have been used to good effect to sort of characterize the relative impact using things like a spider diagram of certain uncertainties with respect to certain variables. How much of an impact does a 10% uncertainty have on a model outcome? There's some good experiments or models that I should say with associative parameter variation experiments that are available through the AnyLogic how-to models. And one of them we're going to be actually opening up for our next exercise with calibration. So I'd like to suggest that we open it right now because it also is germane to sensitivity analysis. So if you were to go here and I'll save this away. If you were to go to example models within the AnyLogic interface here, they shift the location of some of these models around, and so I'm going to seek to find it. My intuition was correct in recollection that it's down in this area still. SIR agent-based calibration. Do you see that? You have to scroll down here to find it at the bottom. Sorry, not the bottom, but it's down in the S's. And if you need a TA, raise your hand, and they will come to your aid. Okay. Okay. So the SAR agent-based calibration we'll use in a few minutes to illustrate calibration processes, but it also includes a parameter variation experiment that's quite helpful for understanding some of the impacts which changed assumptions can have on model outcomes. So most of this I've already covered. Just looking for any slides that might extend important points. Right. So if we have many parameters that we are varying, so the capacity to explore the full space is difficult. Well, conceptually, it might seem desirable to explore all simultaneously. At a practical level, there's a limitation. There's what's called the curse of dimensionality. If we have, say, 2 parameters, let's say 3 parameters, each of which can have 2 values, which is a very small number of values for each, we'll already have 8 possibilities. It's going to be 2 times 2 times 2. If we had 4 parameters, it would be 16. Yes, it would be 16 possibilities. And of course, if those were explored not as 2 possible values each, but 10, it'll go up as 10 to the number of parameters. So with simply 4 parameters, we'd have 10,000 possibilities. And at a certain point, it becomes infeasible to exhaustively examine. And there's some techniques of several types for exploring this. Monte Carlo techniques, drawing them from a distribution, rather than trying to explore an entire hypergrid of possibilities. Judiciously selecting combinations that matter, orthogonal arrays, Latin hypercubes, n-dimensional analysis, to allow us to narrow the number of parameter values to be more meaningful. I don't have time to go into all of these. Suffice it to say that if you were interested in exploring Latin hypercubes, AnyLogic's database functionality, which I'll refer you to here, it's used in a number of the models or at least some of the models we've given you. If you go to these models, you'll notice there's a database area of the model, and you can create or import a table. Often that's used with GIS to import GIS, like location of certain resources if they're not available through online data sets. It might be used to specify the initial values of a population. But one of its other uses is you could specify in a database table values to use to explore for different parameters for successive values of an index, which perform a Latin hypercube exploration. A key with the Latin hypercube is that you explore each value of a parameter is explored, or each range of values is explored at least once. But you don't explore all possible combinations of them. You explore each range of each parameter at least once, you get to it at least once. But with some other combination of the other parameters, you're not as concerned with. Orthogonal arrays basically have you exploring each pair of values at least once, or pair of ranges. These are valuable mechanisms. You can get tools to create them for you, an orthogonal array or Latin hypercube for n different parameters. And you can then put that into your database or put it in an external file, read it into the model, and go through them one by iterating an integer parameter. Okay, it's more advanced topic than we have time to go into today, but TAs can help you explore this in greater detail. Okay, so I provided you. Actually, I discovered these were missing from the site. We're going to be doing a full scan over different slides to make sure you get all of them, and these will be a set that amongst those that I make sure you get provided for hopefully by your departure in the next day for you to be able to have reference. Okay, there's AnyLogic has some logic for performing replications as well that I don't have time to go into, but basically try to limit the number of realizations to a certain count that will achieve a degree of statistical accuracy for calculating things like means. In some of my other presentations, I cover this, and you can find presentations of mine on YouTube that will cover this in more detail. Okay, I'm going to continue on, bearing in mind the time, to a coverage of some basics of calibration, okay, model calibration. Are there any questions that I could address with respect to either the practicalities of use of sensitivity analysis within AnyLogic or use of it to explore stochastics prior to my transition to discussion of calibration? Yes?
So you mentioned you have videos. You talk in those about the best practices for actually reporting those in manuscripts, for example?
This is a good question. Because I've covered it in so many boot camps now and so many classes that I'm trying to think back to the different events. There's a possibility that some of those online would have that, but I can't promise that. And what I could do is offer to to see if I could provide you some references that would spell this out. Within the health sciences, there's a growing attention, rightly so, to codifying best practices, and I'm part of some panels that do that, both as a sort of one of the guides in organizing and delivering on an NIH panel in the U.S. as well as for ISPOR, the International Society for Pharmacoeconomics Research. And there's some additional guidelines that have come out from others. I'm trying to remember the degree to which they specifically focused on, best practices in reporting parameter variation. But I will see what we could assemble for you with respect to this, and see if we can impart some comments, because that would be an asset we could offer to future attendees, and I'd like to see if we could do that. So if one of the TAs could remember to remind me about this as a post-boot camp task, to sort of assemble what we can for resources there, we could add them to the resources for participants. So thanks very much. Yeah. Great. Other questions? Yeah, I do have a lot of coverage of me online on some of these topics, sometimes for calibration with multiple lectures on the topic that you'll find on YouTube. But these days, I have somewhere between 2,000 and 2,200 or something videos, and so it's a little bit hard sometimes to wade through them. Even on calibration, there might be a dozen. So I've got to be careful in terms of trying to suggest to people where to find things, because I don't want to search it through a haystack. Yeah. Other questions? Okay. Yes, John.
Is there any the rule of thumb of like how many iteration or the simulation is required?
So let me parse that into two possible interpretations, and you can clue me in, John, as to which you had in mind. Are you asking how many realizations do we have to run the simulation to develop confidence, degree of confidence in the results?
Yes.
Okay. Yeah. So yes, there are. There is some understanding there, and gosh. So Jeff tells me, Jeff is the font of great wisdom, and he has commented before that the challenge with my boot camps is trying to figure out the 95% I don't cover on a given occasion. And this is one of the things that I realized, oh yeah, I didn't cover that. I really should. We're working hard and doing some thinking during this boot camp about ways we can up our game considerably for future ones. So when I work with these models and we're publishing results, particularly findings from our studies, this is a very practical question. Yeah, what's the size of the ensemble, disciple ensembles, the number of realizations we run? If what you're doing is simply taking means of certain quantities over many runs, there's well-known statistical analyses that you can bring to bear concerning the standard error associated with the means that you can leverage. For a lot of our needs, we make use of non-parametric statistical tests that will help us make sense of these results, so that we're not merely operating in terms of the mean, we're operating in terms of the broader distribution. And if we're dealing with something, for example, like where we're comparing two interventions, and we're trying to see if one intervention has yielded a statistically significant reduction in the cumulative number of measles cases, over a 5-year period or something, we'll end up making use of a Mann-Whitney one-way U test or a Kolmogorov-Smirnov test, for example, to do the testing, where for each, as the inputs into that, you have vectors of values where the length of that vector is the number of realizations you run it. You get one output from each. And that can clue you in as to start to clue you in as to sort of how suitable the number of realizations is for demonstrating significance. We sometimes will pursue that adaptively. We'll see, okay, is the p-value getting close to the threshold or well below it, to guide us, okay, do we need a lot more runs to develop the requisite statistical confidence, if you see what I mean. So we're often doing tests there, and sometimes they're directional tests, sometimes they're not directional tests. We're trying to analyze, are these drawn from the same distribution? But we're using non-parametric because the outcomes from these models are not neatly Gaussian distributed. They're not neatly normally distributed typically. They exhibit, they exhibit asymmetry, they're multimodal, etc. And so the non-parametric tests are mostly what we use, and we will sometimes use them in an adaptive way to test, are we getting enough samples to reliably demonstrate an effect, and if not, we'll sample more. Occasionally we'll go into the thousands of realizations. And I will say this, you'll notice that up here, and this gets to a question that was raised earlier. Up here, there's an indication of cloud. Do you see that? And I had made some utterances about this earlier, but it maybe bears re-emphasizing that. Particularly when it comes to running large so-called ensembles of realizations, running it again and again. And even for parameter variation experiment, where you're varying assumptions about parameters, there's a lot of what we call embarrassing parallelism there. It's embarrassing. It's just so obvious to take advantage of it that if you're not, you're shortchanging yourself. And AnyLogic does a pretty good job of doing that on your computer with running things in parallel. So it can run 8 things at a time on your computers there. That really speeds up the analysis. But there's limits there based on how much is on the computers. And so we do a lot of our work, and Winchell is the king of it, and Wade is the prince, and Narges is a princess, of doing work across large bodies of machines. Okay, so we'll do simulations across the machines, for example, here in this room and through there, and so on a certain day, we'll spawn these jobs out and they'll run in parallel. In other cases, people run things in the cloud. We haven't done much of that with AnyLogic, mainly because we have our own ecosystem and have our own machines and so on. But AnyLogic has made it much easier to run things on the cloud now. So by cloud, I mean you just tap into machines out there on the web, and it's running things. And it's running your model in parallel out there. I can't speak from the authenticity of direct experience with this, but if this were a strong interest from people, let me know. I would say if 4 or 5 people express interest, I'll have one of my TAs do a little presentation on it by tomorrow, so you could talk about it. And for those who can't be here, we'll record it. Okay, so we can comment on that. But just be aware that when it comes to this issue of identifying are there enough realizations, you're going to want to be prepared to do large numbers if necessary. And that may require tapping additional resources if you don't want to take a long time to run them. Those are some comments there. I don't feel I've done it at full justice, but I do want to get onto the calibration before lunch here. Okay? Yeah. Some of these issues come up in the calibration front as well. Okay, so